Okay. So I all we start. So well, if you are here, I guess that you heard about the recently reported NANOGrav anomaly, quote unquote. And as we did last summer for the xenon anomaly, we decided to dedicate a session to discuss this result. But contrary-wise, this time we'll start with an introductory seminar because the topic is a little bit off compared with what we do usually in high energy physics. And Professor Alberto Sesana from University of Milano Bicocca kindly accepted to teach us the basics. And after Alberto, Ville Vasconen will discuss cosmological implications of this anomaly, assuming it's true. So this plan sounds very exciting. I suggest to start, and Alberto, I give you the floor. Enjoy.
Okay, thank you. Thank you for the kind invitation. Let me just share my screen, desktop one. Okay, now, where are we here? I was deleting stuff from my slides. Now you've seen all the talk already, perfect, done. Slideshow. Okay, let me move the bar on the side. Okay, is that all right? Can you see it fine?
Yes.
I presume so. Okay. So thanks for the invitation. And in this 35-40 minutes, I like to tell you a little bit about pulsar timing. How do we use this technique to detect, hopefully detect gravitational waves, how it can be used to detect gravitational waves, what kind of signals we expect to see astrophysically. There will be a talk about cosmological implication later on. And I will spend some time talking a little bit about what's reported on this archive posting from the NANOGrav collaboration. Okay, so this is essentially the plan of the talk. I will talk a little bit, slightly, larger than usual introduction about using pulsars as clocks for gravitational wave detection. Then I'll dive in a little bit into the astrophysics of supermassive black hole binaries, which are the primary targets for this, detection technique. And then I will talk a little bit about the, the predictions and the limits that we placed so far with pulsar timing, and how this NANOGrav feature is framed into this context. Okay, so, well, there's a lot of high energy physicists here, so you're probably familiar with pulsars. And for what concerns this talk, pulsars are not interesting for their own, let's say, physical properties, but they are interesting because they are essentially perfect clocks. Okay, so those are spheres of matter, very dense matter of 1.4 solar masses, more or less, and 10 kilometers in size. They rotate very rapidly. They have a huge moment of inertia. So essentially, their rotation is very, very stable. And in particular, there is a family of pulsars, which is the so-called family of millisecond pulsars, that has a period that is much shorter than the typical normal pulsar, that is of the order of few milliseconds. And what you see here is the famous, among astronomers, PP dot plot of the pulsar. So this is the period, spin period of the pulsar on the x-axis, and the spin period derivative on the y-axis. And you see the bulk of the pulsar population sits up here at periods of order of a second, but there is this family of millisecond pulsars with periods that range from few milliseconds to few tens of milliseconds. These systems are essentially spun up by accretion from a companion, and that's why they essentially, almost all of them, they are found in binaries. And you see the circles here, means that the system is in a binary. You see that most millisecond pulsars are in binaries. So what do you do when you have a perfect clock? Well, you use it to take time, right? So what we do with pulsars is pulsar timing, which is pretty much self-explanatory. So we observe a millisecond pulsar in this case, and we can record essentially the time of arrival of each pulse, as you see here in the lower panel here. This is not a millisecond pulsar, it's a regular pulsar, but you know, it doesn't really matter, it's the same, right? Then you build a model for your time of arrival, and then you subtract your model from what you observe, and what you're left with is a residual. And the residual essentially tells you whatever, you know, stems from the fact that there might be noise in your observation, or there might be, you know, some effect that you didn't account into your timing model. For example, if a gravitational wave passes between you and the pulsar. So if you have a perfect model for your pulsar, and if you have ideally noiseless observations, this residual ideally would be zero, okay? And whatever interesting physics we are interested in, especially gravitational waves, essentially is contained in this residual. So let me go a little bit deeper into this process. Okay, so essentially the pulsar is a neutron star that emits this radio jet, and if the radio jet intersects the line of sight with the Earth, essentially you see this lighthouse effect. Okay, so you can connect. You have very, very precise ticks, and you can connect. You can essentially collect the time of arrival of each tick. Okay, so your pulsar emits your radio beam. This is collected by giant radio telescopes across the globe, and those signals are processed, and they undergo some technicalities like the dispersion and folding of the signal. But you know, we don't go into this; it's just technical. But what you get is essentially a profile of the pulse and a time of arrival, which is the weighted mean of the profile or the peak of the profile, depending on how you want to define it, okay? And then you connect the time of arrival of each pulse. So these pulsars are so precise that essentially you can write the nth rotation of the pulsar as a function of the frequency of the pulsar and its frequency derivatives, okay? So the nth time of arrival, the nth pulse of the pulsar is n0 plus nu tau, plus 1/2 nu dot tau square, etc., etc. So you can, once you know, if you know nu dot and nu double dot, okay, you can predict each pulse arrival time of each pulse, okay? You can invert this relation, and essentially you can determine the time of arrival of each pulse once you know the frequency and its frequency derivatives, okay? The frequency of the pulsar and its frequency derivative. In fact, you don't know this beforehand. What you do, you construct a timing model. So you start to see a pulsar, and then you predict when the next pulse will arrive, and you adjust the frequency and the frequency derivatives in order to match the next time of arrivals. And as you collect more and more data, you refine that timing model, and you measure very precisely the period, the frequency of the pulsar, the first derivative of the frequency, the second derivative of the frequency, and so on and so forth. Not only this, because you know, when you construct your timing model, you have to consider also all the emission and propagation effect of those pulses. So for example, we saw that most of those pulsars are in binaries. And if you're in binary, you have to consider things such as the Einstein delay, the Shapiro delay, the Romer delay. So these are all effects that affect the time of arrival of your pulsar, and you can very carefully measure and you can include in your timing model, and you can measure all of them. I have some examples about how you measure these effects later on. In reality, though, what you do is to refer the time of arrival of your pulse not to your telescope, but to the solar system barycenter. Okay, you need to refer those time of arrivals to a, you know, ideally inertial frame. So what you do, you transform this arrival time at the telescope into the time at arrival at the solar system barycenter. And in doing that, there are a series of corrections that apply. One of which I will talk about later, is the solar system ephemeris. So essentially, if you want to transform the time of arrival into the solar system barycenter, what you need to know is where the solar system barycenter is. And it turns out that essentially with pulsar data today, we are sensitive to uncertainties, to errors in the position of the solar system barycenter of the order of several meters. Okay, so and we can detect these in our timing data. So essentially what you do, you keep timing this pulsar and you build a more and more sophisticated timing model, including all the pulsar frequency and frequency derivatives, all these Romer, Einstein, and Shapiro delays. You have to fit for the pulsar position and proper motion because that also impacts the time of arrival. You need to consider the dispersion measure. So the fact that your pulses travel into the interstellar medium and they're scattered off the interstellar medium, and we will see that this has an effect on the time of arrival. And you have to consider all correction given by offsets of your clocks, transformation of the signal into the solar system barycenter, and so on and so forth. So essentially you build this timing model and you fit the model parameters and you predict the next time of arrival of your pulsar, okay? And you do this over timescales of tens of years. We have pulsars that have now been timed by, 25, 30 years or so, okay? So just to give you some examples, so suppose that in this timing model, you get the frequency derivative of your pulsar wrong, okay? Then the difference between your timing model and your time of arrival will appear like a parabola shape, like this in the top right, okay? This is the residual. If you get the frequency derivative wrong, you see this shape in your residuals, okay? If you have the position slightly wrong of the pulsar, you have a sinusoidal behavior in your residual like this, given by the fact that this is the rotation of the Earth. You see that these are 1 year periods. And if you get the wrong position of the pulsar, you see, you see these errors in the time of arrival that are estimated by your timing model. Or if you screw up the proper motion of the pulsar, so the pulsar is moving with respect to where you think it is, you have these increasing and decreasing sinusoidal shapes. So you see every little error in your timing model shows up in your residual. When you fit for everything perfectly, what you're left with is essentially a white noise, like the one that you have in the top left. Okay. Another complexity, technicality, is the fact that these pulses travel into the interstellar medium and they are slowed down depending on what is the frequency of the pulse. So here you see a radio frequency on the y-axis and pulsar phase on the x-axis. And you see that the highest frequency arrive earlier with respect to the lower frequencies. And the pulse profile is much more narrow, is narrower, okay? Whereas at lower frequency, it is broader, okay? And this is due to a refraction into the interstellar medium. And this is something that you have to fit for. Essentially, this is a quadratic function in frequency. You fit for this quadratic function and you align all the timing residuals and you get all the, the time of arrival, and you get the time of arrival of your pulse. Another effect, another example is the Shapiro delay. Since you are, most of these millisecond pulsars are in binaries, when the pulsar is between, when the companion of the pulsar here in the top right is between you and the pulsar itself, then the pulse travels into the potential well of the companion, which acts essentially as a refraction index, okay? And this slows down the pulse, and the pulse arrives later with a delay, which has this typical narrow shape. And this is very interesting because, for example, it allows you to measure very precisely masses of pulsars. And in fact, one of the most massive pulsar of two solar masses was measured. Its mass was measured through this Shapiro delay technique. Okay, so this is just to give you an idea that the timing model is very complex, includes a lot of effects, which are kinematics, kinematic, Newtonian, but also relativistic. And you can actually measure a whole lot of parameters for your pulsar system, okay? When you've done all of that, essentially, you have your model prediction, which is the blue line here, when you fit everything, and you have the actual time of arrival with noise, which is the red curve here. And what you're left with is some residual, because of course your model cannot be perfect. There's noise in the data. This residual we saw before, you know, if everything is perfect, but there is just noise in the data, it's just it's just a random walk, a white noise. And there might be some physics that you didn't take into account in your timing model that might create some extra residual. And this, for example, can be the passage of a gravitational wave. So let me just consider what happens when you have a gravitational wave passing between you and a pulsar. So now suppose you have the Earth here, okay, in the top, when looking at the top right cartoon. There is a pulsar there, okay, and suppose here at this end we have the Earth and the pulsar is at the other end, and I have a gravitational wave going through. So in this cartoon here, the gravitational wave is traveling into the screen or outside the screen, whatever you prefer. So you see that the space is stretched and squashed between the Earth and the pulsar. So the pulses arrive to the Earth a little bit earlier or a little bit later. So the residual, which is what I plot, is the red line that I plot in the bottom panel. Essentially, that with respect to, you know, zero residual, your time of arrival will arrive a little bit earlier or a little bit later, depending on whether you are in a squeeze or a squash of your passing gravitational wave, okay? So what you expect is that if there is a gravitational wave passing between you and the pulsar, you would have this dephasing of the pulsar, arriving a little bit earlier, a little bit later, depending on the phase of the wave, okay? Now, in reality, this is just an oversimplified cartoon. The fact is that pulsars work in the short wavelength limit, in the sense that the distance between the Earth and the pulsar is actually much shorter, is actually much longer than the wavelength of the waves that we are measuring, okay? So essentially what happens is that when the gravitational wave passes by, the geodesic along which the photons travel is modified, okay? And then you have to do a path integral, an integral over the path of the photon. And what you get is essentially that, you know, you get an integral of the geodesics, you get the shake at the pulsar end and the shake at the Earth end. And this dephasing is proportional to the amplitude of the wave at the pulsar and the amplitude of the wave at the Earth. And the residual is essentially just the integral over time of this dephasing, okay? And again, this is a sinusoidal wave. The residual is the integral of the strain, which is a sinusoidal wave, so it's itself a sinusoidal wave. So what you expect is this residual to be an oscillatory function. And if you now take a typical astrophysical system like a supermassive black hole binary of 1 billion solar mass, relatively nearby, a few hundred megaparsecs, say, emitting at a frequency of a few nanohertz, what you get is that these residuals are of the order of 10 to 100 nanoseconds, which is exciting because this is exactly the kind of precision we can time the best millisecond pulsars nowadays. So really, timing of millisecond pulsars has the potential of detecting these low frequency gravitational waves from in this case, from a cosmic population of supermassive black hole binaries. So one thing that I can say it here, if I plot now the astrophysical landscape of gravitational wave, I can compare this technique of timing pulsars to other techniques like the ground-based interferometers, such as LIGO and Virgo. So those detect, so you see frequency here on the x-axis and characteristic strain amplitude on the y-axis, the amplitude of the wave. So you see that LIGO and Virgo operates in the audio band from 10 Hertz to some kilohertz at low, and they are sensitive to stellar mass binaries like stellar mass black hole, binary neutron star, and so on and so forth. If you move to lower frequency in the milliards regime, we will have in a decade or so, hopefully, the laser interferometer space antenna, LISA. So I should remove the E here. And this is sensitive to a wide range of gravitational wave sources, from galactic binaries to extreme acceleration spirals to the in-spiral emerger of moderately massive supermassive black hole, like between 1,000 and few million solar masses. Pulsar timing sits at even lower frequencies, okay? And why is that? Well, the reason for that is twofold. So essentially what we're using as our detector is to detect this source is a time series of time of arrival. And these time series are, let's say 10 years long or so. So the minimum frequency you can probe is the inverse of the length of your time series, which is of the order of few nanohertz, okay? At the higher end, what happens is that we don't have the capability, the instrument and the time to observe continuously any millisecond pulsar, okay? So essentially what you do, you take a time of arrival of each millisecond pulsar once a week, once a month, okay? So the maximum frequency you can generally probe is of the order of hundreds of nanoseconds. So really, pulsar timing is a technique to detect nanohertz gravitational waves, okay? And the primary astrophysical system of such waves is a cosmic population of in-spiraling supermassive black hole binaries, okay? So let me talk a little bit about this cosmic population. So essentially, why this is interesting? Well, first of all, because we know that supermassive black holes exist at the center of galaxies. So whenever we had the capability, the resolution to pierce into a galaxy center, we always saw a supermassive black hole, okay, there. And we see these supermassive black holes shining as quasars up to redshift 7. Okay, so we know that these things are already in place at high redshift. And how do they come about? Well, according to our best understanding of structure formation, the formation of galaxies is hierarchical. So here you see a cartoon. This is a merger tree extracted from a semi-analytic model put on top of a numerical simulation of a formation of a large galaxy. So the big dot here is the large galaxy at redshift 0. And as you go back in time, you see how these decompose into its progenitor. So essentially, the model is that big galaxies today are formed from the merger of smaller galaxies into ever larger structures and accretion of gas from the intergalactic medium, okay? So these galaxies grow also because of galaxy mergers. In the top left, right, you see scaling relations that are measured between properties of those galaxies, like the mass of the stellar bulge of these galaxies, or the velocity dispersion, which is the typical velocity at which stars move in the stellar bulge, and the mass of the central supermassive black hole. And you see that there are, relatively tight correlation pointing toward a coevolution between the black hole mass and the properties of the host galaxy. So the model goes as follows. So if galaxies form hierarchically, and if we have somehow some seed black hole in these proto-galaxies at high redshift, during galaxy mergers, these black holes will come together, form massive black hole binaries, and merge, forming ever larger black holes. So essentially, it's by starting from seed black holes of hundreds to hundreds of thousands solar masses, depending on the model, we can build up through a series of mergers and accretion events supermassive black holes of billion solar masses that we see today. Now, we don't know, in this model, supermassive black hole binaries inevitably form, but we don't know much about them. We don't know what's the nature of the first seed. We don't know how they grew up along the cosmic history. Of course, there are a lot of constraints from the quasar luminosity function, for example, and so on and so forth. But really, the process of merger, of massive black hole binary merger, is it has very, very few observational constraints. Okay. Now, let me go back to the typical signal that you might expect from such a binary. So, as I said, you have the signal that you expect, the phasing that you expect to see in the pulsar is proportional to the amplitude of the wave at the pulsar and the amplitude of the wave at the Earth. So essentially it's a superposition of two sinusoidal waves. So here are just mock residuals that I produced from some binary massive black hole. Okay, if the binary is circular, you get something like this. If the binary is eccentric, you get something far more complicated because the emission of gravitational waves depends on the phase of the orbit. It's much stronger close to a periastron and is much less efficient at apoastron. So you have a much more complicated shape. So what you're looking for is something like this into data that look like that, okay? So those are the timing residual once you subtracted the best timing model that I showed you before, right? In fitting for all the frequency and frequency derivatives of the pulsar, interstellar medium dispersion, and all sources of noise you can think of. These are, for example, 20 pulsars from the Parkes pulsar timing array. So this is an Australian collaboration looking for these objects. So we are looking for, this type of signal in this time series. Actually, it's much more complicated than that because we don't have an individual supermassive black hole binary in the universe, but what we have is the whole population of slowly adiabatically spiraling supermassive black hole binaries. So if you take a picture of the sky, what you have is a population instantaneously at each time, you have a population of massive black hole binaries that are emitting at different masses, at different redshift, and at different frequencies. And if you do the math, essentially, all their signals add up in quadrature, if you wish. And what you expect to see is a typical strain, which is a sort of, is a stochastic signal, which has a power spectrum that goes with the frequency to the minus 2/3. So the typical strain of the signal we expect, it is characterized by an amplitude and a frequency slope, okay? And a frequency f to the minus 2/3. And what you see in the bottom panel here is essentially the contribution to this signal from a population, from a mock population that I made like, 8 years ago or something. So you see contributing to this signal is a huge number of massive black hole binaries of hundreds of millions to billions solar masses at relatively low redshifts, okay? And if you just compute the signal, it looks something like this. Here, you have frequency on the x-axis and characteristic strain of the signal on the y-axis. Each blue triangle is an individual binary, and the signal here, the overall signal, is essentially the green curve. So you see that there are, it's a sort of stochastic background / popcorn noise in a sense that as you go at low frequencies, you have a contribution of many dim sources and you sit onto this theoretical f to the minus 2/3 power law. But at high frequency, essentially, you are likely dominated by, sources are sparser, and you're likely dominated by nearby loud sources, and you might actually detect supermassive black hole binary individually, okay? But inherently, pulsar timing arrays are more sensitive at lower frequency. So what we expect to detect is essentially this incoherent superposition of gravitational wave signal that forms this stochastic pattern. Now, if I take this signal and I inverse Fourier transform it and I inject it in a pulsar time series, this looks like the red curves here. Okay, so you see it's a typical red noise. You see it here. This is a different pulsar, and then I put some white noise on top to mock some, pulsar observations. So if I take a random pulsar, it might look something like this, the residual that I get. So you see some very long wavelength red noise. So is this a gravitational wave? Well, not so fast because, pulsars are precise clocks, but they do a whole bunch of things that we don't know about, okay? And in particular, pulsars are known to have intrinsic red noise. It's also called timing noise. So it's very hard to say, okay, you see some red noise in your pulsar time series, that's a gravitational wave. What you need to do is to cross-correlate signals from an array of pulsars. And this is where the concept of pulsar timings array comes from, okay? And the idea is the following. If you have time of arrival of two different pulsars in the sky with an angle alpha between them, theta between them, let's say, the time of arrival, the residuals in the time of arrival in the presence of a gravitational wave background are correlated in a very specific way that only depends on the relative angle between the pulsars. And this was worked out by Hellings and Downs in 1983 and is known as the Hellings and Downs correlation, Hellings and Downs curve. So in particular, you see that if the two pulsars are in the same, let's say, region of the sky, the time of arrival is positive, the residuals are positive correlated. If they are at 90 degrees, become negative correlated. And if you are in opposite direction, it's still, you know, positively correlated. So now this is a complex, the actual shape of this curve comes from a complex double average over pairs of pulsars and over, you know, directions in the sky. But you can easily at least get a grasp of why this is from the quadrupolar nature of the gravitational wave. And simply like this. So suppose that the Earth is in the center here, okay? And your gravitational wave is stretching and squashing the space like the GIF is showing here. If your two pulsars up here are in the same location, okay, they see essentially the same gravitational wave effect. So if there is some residual that is due to a gravitational wave signal, it has to be positively correlated between the two pulsars, okay? But if the pulsars are at 90 degrees one another, then, you know, when one experiences stretch, the other experiences squash. So you expect the residuals coming from gravitational waves in these two pairs, in this pair of pulsars, to be negatively correlated, okay? And the same reasoning happens if you are at opposite direction. Again, stretch and squash at the same time, so still you get residuals that are positively correlated. So this gives you a visual understanding on why you expect this specific correlation in the residuals. And what we are looking for in pulsar timing data is this correlation pattern in our pairs of pulsars. And this is what we consider the smoking gun for a detection of a gravitational wave signal. And this is important as I dive into the final part of my talk. So I come to the NANOGrav paper. So let me skip some time. So we need many pulsars. So what we need are large collaborations and large radio telescopes. There are three main collaborations in the world: European Pulsar Timing Array in Europe, NANOGrav in North America, Parkes Pulsar Timing Array in Australia, and in Australia, there is an Indian Pulsar Timing Array joining the effort, a Chinese Pulsar Timing Array as well, and all these collaboration join forces in the International Pulsar Timing Array, okay? We are timing overall 70, 80 precise millisecond pulsar, many collaboration time, you know, also the same pulsars, the best pulsars are in common from all collaborations. And what we do, we build our data series, we look for a gravitational wave signal, we don't see much, and we place upper limits. And this is the progression of those upper limits as a function of time, okay? Compared to prediction of several models I found in the literature from 1995 to today, okay? So you see, we are placing upper limits that are becoming very interesting, but still consistent with prediction of astrophysical models. This is an example of a non-detection from 2015. We used the 6th best pulsar of the European Pulsar Timing Array. And here you see this correlation pattern, okay? You see our data points 5 years ago were perfectly consistent with the Hellings and Downs, were perfectly consistent with 0, and we call this an upper limit, okay? Let me skip this part because I want to go to the to this point. So you might have noticed that in the last few years, actually, these limits didn't quite get more stringent, okay? We are somewhere stuck in the range of 1 to 2 to 10 to the minus 15, okay? And this essentially is, can be a hint that, you know, there might be something in the data, because if there is some correlated, suppose there is a gravitational wave signal in the data, this will show up as some correlated red noise that we cannot feed out of the data, okay? At the beginning, it's gonna be very hard to probe the Hellings and Downs correlation. And until we have that, you know, it's very hard to talk about the detection of anything, okay? It becomes some interesting feature in the data. But, you know, we might be at the start of that process. But let me tell you, in the last few minutes, what is in this NANOGrav preprint and what the significance of it. So first of all, let me start from those limits. So you saw those limits from 2016, 2018, they start to get around 10 to the minus 15. However, there's a catch for each of these limits. For example, Shannon 2015 is essentially a single pulsar limit. So they use 4 pulsars to place a limit on the presence of a gravitational wave signal. However, one of those pulsars was much better than the others. And what you do when you build your timing model, you fit for the intrinsic noise of the pulsar. And now, if you don't have if you have a pulsar that is much better than the others, you will always fit out whatever red noise is in that pulsar as intrinsic red noise of that pulsar, because you cannot really cross-correlate it with any other red noise in any other pulsar, because your other pulsars are much worse, okay? So this limit, it has been known for a long time to have this issue of essentially overfitting the red noise of their best pulsar that we had. Arzomanian et al. 2016-2018 started to see interesting common red signal in their data. And this is when the problem with the ephemeris, solar system ephemeris came about. So essentially, much of the common red process they've seen stem from misplacing essentially the solar system barycenter. So what happens is that if you get the orbit of Jupiter, the position of Jupiter or Saturn wrong by, hundreds of meters, that's enough to show up in your timing residual. Now, the thing is that this shows up as essentially as a correlated red noise. The thing is that if you think about it, this is the motion of a planet in a planar orbit. So this this red noise has to be correlated, has to have essentially a dipole correlation, okay, in pairs of pulsars, because essentially your solar system barycenter is moving a little bit, forward and back, okay? So it's a dipolar correlation, which is different than the Hellings and Downs correlation. However, when you have points like, well, the one that I showed before, it's very hard to distinguish between a dipolar and a quadrupolar correlation. So, it's this solar system ephemeris is actually a problem, okay? So essentially we've seen some common red signal coming about in these previous papers, but most of these was attributed to uncertainties in the solar system ephemeris and other issues with the timing model of the pulsars. So in the NANOGrav 2012.5 year paper, what they did an analysis of their 12.5 year data set. So they added a couple of years of data to their previous data set. They are timing 43 millisecond pulsars. This is important because the more pulsars you have, the more pairs of pulsars you can use to populate these Hellings and Downs curve, okay? And what they use advanced scheme to account for the solar system ephemeris and all other sort of noise. And what they have is a clear, pending obviously any possible issues with their analysis that I'm not aware, and I don't have the data to check that. What they have is a clear detection of a common red process. So this means that this is a red process, it has a red spectrum, and this process is consistent with something that is common across all pulsars, okay? So it is not different from pulsar to pulsar, okay? And this common red process, you can describe it as an amplitude and a frequency, because you really have 2-3 frequency beams. You cannot do much else than fitting a power law. And if you think that is a stochastic background from gravitational waves, the amplitude that it would have is 2 times 10 to the minus 15. So it's up here. essentially more or less where the most recent upper limits were, okay? And it's, you know, it's kind of high, but it would be still consistent with the signal coming from an astrophysical population of massive black hole binaries, if it was a gravitational wave signal. Now, let me say a little bit more about this. One of the things that I stressed is that it's very, very important to detect the spatial correlations between these in different pairs of pulsars, okay? Because the real smoking gun of a gravitational wave signal would be this quadrupolar Hellings and Downs type correlation. This is what they cannot claim in their data yet, okay? So what they do is that they claim that they have this common red process, and then they say, okay, it's common in our pulsar, but is it uncorrelated, or is it correlated with different correlation patterns, okay? So put in other words, if this is uncorrelated, suppose this is zero correlation, okay? Those points would be just scattered around zero. This would be an uncorrelated common red process. If it's correlated as a gravitational wave signal, this would follow the Hellings and Downs curve here, okay? If was correlated as a ephemeris noise, this would have a dipolar correlation pattern, which is not plotted here, but would be something that is positive at small angles and negative at larger angle, okay? So what they show in their Bayesian analysis is that either monopolar or dipolar correlations are disfavored compared to an uncorrelated common process, okay? So you feed the data with an uncorrelated common process is much better than assuming that is correlated as a monopole or as a dipole. So the dipole correlation would stem from errors in the solar system ephemeris. The monopole correlation would stem from clock errors. If there is a offset in your clocks, that would affect all the time of arrivals of all your pulsars in the same way. So you would have a monopolar correlation. So this would be a correlation that is the same in all pairs of pulsars, okay? They don't see evidence of that. However, if they contrast no correlation compared to Hellings and Downs correlation, they get inconclusive evidence, okay? The bias factor they get is close to zero. So there is a common red feature, okay? This common red feature is not monopolar or dipolar correlated. Sorry, can you hear me?
Yep.
Yeah.
Sorry.
It doesn't show evidence, at least yet, at least in this preprint, of an Hellings and Downs correlation. So what's the future ahead? Well, the future is that we have, first of all, you know, NANOGrav is only one of the pulsar timing collaborations that are operating, and all collaborations have their own data sets, and they are investigating, in fact, you know, red features in their data, okay? It's just that it's a very complicated work. It takes a lot of cares and a lot of analysis. And I would like to actually stress that, you know, this paper by NANOGrav is still in a preprint stage, so it's not published yet, okay? So we need to carefully assess whether there are issues with the analysis, whether the result holds, okay? In the future, we will have Meerkat. Well, it's already operating in the Southern Hemisphere in South Africa, and it will give us a factor of 10, or a few improvement in the timing precision of pulsars in the Southern Hemisphere, which is very important because most of the best pulsars that we have are there. Then we have FAST in China, this 500-meter dish, which is discovering a lot of pulsars in the Northern Hemisphere. And eventually we will have the square kilometer array, which essentially will make us, a tenfold jump in our sensitivity to gravitational waves with pulsar timing arrays. So just to conclude, you know, timing of millisecond pulsars is an effective tool to probe low frequency nanohertz gravitational waves. And the primary suspect for these type of waves at low frequency, at least from the astrophysical side, would be a population of supermassive black hole binaries, okay? Now, pulsar timing is getting very, very good at doing this job, and the upper limit that has been placed recently have been quite stringent, but they might have few issues related to, misplacing of the solar system barycenter, overfitting of individual noise of pulsars, and so on. So there is a likely presence of a common red features of unknown nature, and this common red feature, might actually stem from other sources of noise, but it might also be from a gravitational wave signal. The only way to find out is to see whether by, waiting, adding more pulsar and analyzing other data sets that we are actually doing right now, any evidence of this Hellings and Downs correlation comes up or not. So it's certainly very exciting, but certainly, this is just an interesting feature that is not of a, gravitational, cannot be considered a gravitational wave detection as of yet. And I will stop here because I'm running over time, and I take any question. Thank you.
Thanks, Alberto. The seminar was very clear. Questions for Alberto?
Sorry, I have a stupid question. Can I ask?
Please go, Alessandro.
So this angular correlation is absolutely needed if it's a gravitational wave, or you can avoid it by having many waves going in different directions and different frequencies and stuff like that.
Sorry, can you repeat the question? What do you mean?
The characteristic angular correlation.
Yes.
So is this absolutely needed if it's a gravitational wave, or maybe it's something that you can avoid if you have many waves that come from different directions and so on?
No, it's something that it's always there. I mean, you can actually show that even if you have an individual source and you have enough pairs of pulsars, actually these quadrupolar correlation shows up because it's intrinsic into the quadrupolar nature of gravitational waves. And as long as you don't see that, it's actually going to be very hard to convince anybody that you've seen a gravitational wave signal. Because, pulsars are very precise clocks, but we really don't know exactly what they do. There are sources of noise that are not very well understood. Dispersion in the interstellar medium is actually still an issue. So as long as you don't, but there isn't really anything we expect to correlate in that way among the sources of noise we can think of. And so, when you detect that, then you are reasonably sure that what you are seeing is a gravitational wave signal. So I would say that is absolutely necessary to see a quadrupolar-like correlation pattern. Otherwise, nobody will believe that.
Actually, a related question. So actually, I got confused. So this quadrupolar pattern for a single coherent source, it's easy to understand, and the intuitive explanation that you gave made sense. But for a stochastic background, when you're looking for wavelengths which are much smaller than the distance between the pulsar and the Earth, this is a very non-intuitive argument.
Yeah, it is, but you have to do the double integral, and that's what happens.
Even for a stochastic background where the wavelength of the gravitational wave is much shorter than the baseline,
yes,
this is still true.
Yes. Yes. Yeah. I mean, as I said, the single wave example is just to give you a picture of why you might expect such a correlation. Then of course you have waves coming from all directions,
right?
But still, nonetheless, these positive, negative, positive correlation remains, and it's due to this quadrupolar nature. Yeah.
Okay. Thank you.
Welcome.
We have a raised hand by Lijing Shao. Can you hear
Hi.
me? Please.
Hi. Hello, Alberto. Thanks for the very nice talk. So you briefly mentioned the prior of these parameters will affect the outcome of the analysis. So can you comment more on this? So does this?
You got me there. I didn't really comment on that, but I had a sentence, right? Yeah. So the thing is that when you do these okay, you know, I don't know exactly what's my audience here, but if you are a Bayesian or a frequentist or whatever, but really the difference between Bayesian and frequentist analysis is that, you know, the choose of your priors in the Bayesian analysis, and this makes the difference when you have essentially, you know, marginal or perhaps no evidence of your signal, right? The real difference is where you might be there detecting something, but you're not sure. And then at that point, what you take as a prior in your analysis actually matters, okay? And what happens, especially in pulsar timing analysis, is that when you think that you don't have a signal in your data, what you do, you use a log uniform prior on the amplitude to place an upper limit. Whereas when you, you know, suppose that it works pretty much, at least, you know, how it's done in our, in PTA data set, it's pretty much like that. So you run an analysis by assuming a log flat prior on the amplitude, okay? And then you don't see exactly, you don't see any evidence for a bump, let's say, at a given amplitude. So then you are convinced that, okay, there's no signal in the data. How can I get the most stringent upper limit from my data set? I just use this log uniform prior to essentially place the best upper limit again. But by doing this, the upper limit that you place might be actually more stringent than if a, let's say, putative faint signal that you might have in there. So you might place an upper limit of 1.5 10 to the minus 15, for example, when there is a signal that is 2 10 to the minus 15 in your data. And in fact, if you look at the posterior distribution of your upper limit and the posterior distribution of your feature, there is a broad overlap between the two. It's not that, you know, the previous analysis was wrong and didn't catch this feature and this analysis is right, okay? So it can be actually that the choice of the upper limit plays a role, the choice of the prior plays a role in the exact value of the upper limit that you put. You know, when you are there with barely marginal signals, you know, anything within a factor of 2 really can be ascribed to the choose of priors.
There's a related question by Enrico in the chat. Has a frequentist analysis been done?
Yeah, because I remember in the previous analysis, there was also a frequentist analysis.
Yes, there has been a frequentist analysis done in all these papers, all the upper limit papers, and also in this feature, let's say paper by NANOGrav, and the results are generally broadly consistent. I think also in this 12.5-year data paper, they have some marginal, well, they have evidence, actually not marginal, they have definitive evidence of a common red process in their data. Yeah, but also with that, with that frequentist analysis cannot say anything about the presence of a Hellings and Downs correlation.
Thank you.
Raised hand by Andrea Caputo.
Hi, ciao Alberto.
Ciao,
Talk. So I have a couple of brief questions. The first one is, if you remember, if they comment about what is disfavored the most between the dipolar and monopolar signal. And the second one is in the plot that you showed of the residual, in the data points, like this I mean, what I think that are the data point is gray lines are like super stretched. And I was wondering if those are errors or what are they?
Yeah. Okay. So the first question, I actually don't remember. There are the numbers in the paper, but they are both disfavored. They are similarly disfavored compared to an uncorrelated red process. The log 10 bias factor is between 2 and 4, depending on whether you fix the solar system ephemeris or you fit for the solar system ephemeris with bias FM. So, so they have a bias factor between 100 and 10,000, disfavoring either of these processes compared to uncorrelated noise. I don't remember on top of my head which one. Okay. One is 4.2 and the other is 3.9 or something like that. I mean, they're both equally disfavored, I would say. And here, so here you're referring to the width of these violin plots.
Yeah.
Yeah. Those are the errors in the measurement of this red process. I mean, this is very generally.
So why, if you go, for example, I would expect that if you go to lower frequency, this means that you will have much less observation time, right?
Mm-hmm.
But they seem like that the errors are smaller, while if you go, for example, let's say around 10 to the minus 8, then you see these violin like that are very, very stretched, and I don't understand why.
Well, yes, but this is a log plot on the y-axis, right? So this is, they're very stretched, but the actual nominal residual there is, 20 nanoseconds, whereas in the upper left, it's like 500 nanoseconds. I mean, it's a log in the y-axis. So it's really, here is essentially what you have here is the white noise of the observations, right? It's like 50 nanoseconds, which is the level of the white noise that they have. So
okay.
So I think, yeah, so this might be but I don't know exactly what they do in the analysis, and I don't know exactly what they do when they produce this plot.
Okay. Yeah, I was just confused by the fact that even if it is a log plot, I would have expected that. I mean, with Pulsar is usually, as you say, right? If you have much more observation, a lot of your folding time like analysis, then you have a very good measurement, right? So I would have expected that the last points were the most noisy ones, right? Why it doesn't seem so.
Yeah, but the problem here is that, so really here, I mean, if you consider the width of these things here, so these are essentially so I don't know actually if they fit out the best model here. So this is like of the order of tens of nanoseconds, which is essentially, the intrinsic stability of the pulse profile. I mean, this is really the width of the timing precision that you can get, really. Mm-hmm. So, yeah.
Yeah, okay.
Okay. I suggest that we move to the next talk and then we postpone.